let's have a closer look at the impedance in an RLC circuit. Remember, we did the phasor diagram. This is XC, XL, and R, and we find the impedance by taking the difference between XL and XC, and this is our Z. And the expression that's given for Z then is square root of R squared plus XL minus XC squared. Now, notice at the fact that XL and XC point in opposite directions, so they are canceling each other out. In particular, there is one case when they completely cancel, when XL minus XC is 0. 0. That's the minimum value for Z. Then it is equal to R. Look what's going to happen to the current for a constant imposed generator voltage. If I have a minimum Z, I'm going to have a maximum I max. We call this resonance. Okay, now if we look at it, remember R is independent of the frequency, XL is proportional to the frequency, XC is inversely proportional to the frequency. This is the overall Z. We discussed the graph here. What we are looking at is, let's see, is this one here. It was in blue and now I'm redoing it with red. The others R is this original one here, XC is this one here, and XL is the yellow one here. Now you notice for a particular value the impedance is at a minimum. That frequency for which we have a minimum in the impedance, we call it the resonant frequency, the resonance frequency. In that particular case, XL is equal to XC. So if we write it up, we are writing 2 pi FL is equal to 1 over 2 pi FC. And we are solving for that F. So moving the 2 pi FC in the other side, so we have 4 pi squared F squared L times C is equal to 1. And then isolating the F, then we have F squared is equal to 1 over 4 pi squared LC, and then taking the square root in both ends, and that's what we get. That's our resonant frequency. That's the expression for the resonant frequency for an LC circuit. Okay. Now, what I mentioned, if we have minimum resistance, that's when we are going to get the maximum power, the maximum dissipated power, the maximum current in the circuit. So the current curve is going to look like the yellow one that we have here. So for any particular combination of values, I'm going to have a different resonant frequency. See, I'm increasing C here and I'm having smaller resonant frequencies. I'm increasing the inductance, and I'm again getting a smaller resonant frequency, decreasing the inductance, and I'm having a larger resonant frequency. You see it's getting wider as well, but then the resistance value does not affect it, but it makes it, the peak is not as pronounced, if you notice. The smaller the resistance, the more pronounced the peak is.